Good morning. It's February 3rd, and this is your daily brief in science. Here's everything you need to know. A bold search is underway to test a fundamental assumption in particle physics. The muonium-antimuonium conversion experiment, or MACE, seeks spontaneous muonium to antimuonium conversion, a process that would violate lepton flavor conservation and point to new physics beyond the standard model. Researchers from Sun Yat-sen University and the Institute of Modern Physics, Chinese Academy of Sciences, with collaborators in China, lead the project. MACE probes delta L equals two processes in leptonic physics using a high-intensity surface muon beam, a novel silica aerogel target, and refined detectors to push sensitivity far beyond previous limits. The conceptual design was published on January 28, 2026 in Nuclear Science and Techniques, with the full study accessible via DOI 1.007/S41365-025-01876-0. If successful, the experiment could open a window to new leptonic physics and access energy scales between 10 and 100 TeV, potentially rivaling future collider reach. Phase 1 will also explore rare muonium decays and lepton flavor-violating processes such as M-arrow-gamma-gamma and mu-arrow-E-gamma-gamma. Beyond fundamental physics, the technologies developed for MACE, muonium production targets, low-energy positron transport, and high-resolution detectors, could find broader applications in materials science and medical research. MACE is part of China's broader push to advance high-precision nuclear and particle physics infrastructures and to foster international collaboration and technological innovation. The project aims to improve sensitivity over the 1999 limit by more than 2 orders of magnitude, targeting conversion probabilities around 10 to 13. Ultimately, MACE is framed as a new window into fundamental laws, with every component optimized to explore physics that could redefine our understanding of matter, symmetry, and the universe. A landmark cell study from Mount Sinai and BPGBIO redefines how we study the aging brain by using living human tissue to map molecular activity to brain structure, not postmortem samples. The researchers analyzed living cortical tissue from 141 neurosurgical patients, combining magnetic resonance imaging with multi-omics data, bulk RNA sequencing, proteomics, and single-nucleus RNA sequencing, to create the first living tissue molecular structural map. This map links real-time cellular biology to brain architecture, including cortical volume, area, and thickness, offering a direct view of aging processes as they happen in living brains. The study positions cellular senescence as an active, regulated program that shapes brain structure across the lifespan, challenging the idea that senescence is only passive aging. It outlines a molecular roadmap for human brain aging, from development through old age, highlighting senescence as an ongoing program rather than a one-way decline. Leaders at Mount Sinai and BPGBIO say shifting from postmortem models to living tissue will speed translation of findings into therapies and anticipate industry partnerships to move this work toward precision therapies for neurodegenerative diseases like Alzheimer's and Parkinson's. The research underpins the Living Brain Project and BPGBIO's causal AI platform NAI, signaling that the data will be explored to inform therapeutic strategies and drug development. The study also notes a disclosure. Eric J. Nessler, serving as a thesis advisor, sits on BPGBIO's scientific advisory board in a compensated role. Overall, the work marks a shift toward live tissue, aging biology, cross-cellular integration, and causal modeling as foundations for translating insights into therapies. In practical terms, the researchers aim to inform precision therapies for neurodegenerative diseases and accelerate translational research by using living human brain biology as the primary reference. The announced direction is to move away from relying solely on postmortem tissue toward leveraging living tissue to better understand disease and guide therapeutic innovation. A new trial tests PaceMe, a digital tool that pairs a Fitbit with a mobile app to help people with long COVID manage energy and avoid post-exertional malaise, but it did not beat standard care in reducing PM. The randomized study enrolled 250 participants, with 125 using PaceMe's full tracking and real-time alerts, and 125 in a non-tracking dummy control over 6 months. While PEM reductions were not superior, the trial shows PACE-ME is feasible, safe, acceptable, and well-received, establishing a framework for future digital health tools in fatigue-related conditions. Lead researchers were Dr. Lawrence Hayes, Dr. Nilahan Sanal Hayes, and Professor Nicholas Sculthorpe from their respective institutions, and the study appears in Nature Communications in 2026 with DOI 10.1038/25-64831-Y. Findings are framed within health policy contexts like the NHS Long-Term Plan and the Darzi Report, signaling digital transformation in chronic illness management. Methodologically, PACE-ME uses real-time physiological data to set personalized thresholds and context-aware prompts, signaling a move toward precision digital therapeutics and remote care. Researchers emphasize user feedback loops to refine algorithms that distinguish safe versus excessive activity and to integrate with multidisciplinary care teams for future efficacy. The NIHR-funded trial compared PACE-ME with full tracking and alerts to a data input-only control to assess impact on PEM and energy management. Over 6 months, both groups showed improvements in overall symptoms and well-being, with participants exceeding their energy allowance by about 50 days. Roughly 13 PACE-ME participants moved from PEM positive to PEM negative, and PEM reports declined by about 10%. Authors suggest adapting the platform for other PEM-like illnesses such as ME/CFS, lupus, and MS, and stress tailoring digital interventions to recovery trajectories in line with NHS goals. PACE-ME is described as a digital tool pairing wearable activity tracking with an intelligent app to help manage energy expenditure and prevent PEM in long COVID. A UC San Diego-led study looks to a consumer smartwatch as a continuous monitor for stress, pain, and craving in people with chronic pain on long-term opioid therapy, aiming to flag high-risk states for opioid misuse before a crisis occurs. Researchers used heart rate variability data from a Garmin Vivo Smart 4 to gauge the nervous system's response to stress, collecting 10,140 hours of wearable data from 51 adults over 8 weeks. They integrated clinical context from medical records, demographics, prescription history, symptoms, and related conditions via compact numerical summaries generated by clinically trained language models to boost prediction accuracy. Predictions were personalized by training individualized models and applying a learning-to-branch approach to identify clusters of similar characteristics, avoiding a one-size-fits-all predictor. The work, published in Nature Mental Health in 2026, as personalized entropy-informed deep learning for identifying opioid misuse, DOI 101038/S44220-025-005558, analyzes daily pattern shapes over time with nonlinear dynamical analysis to estimate misuse risk. Higher-risk individuals showed more repetitive, less flexible trajectories, indicated by lower entropy, compared with those prescribed opioids as directed. The combined smartwatch data and medical context improved model performance and could enable earlier detection of risk shifts between clinic visits, potentially triggering timely, just-in-time interventions. The study envisions ongoing monitoring to support proactive interventions rather than periodic checks, with the aim of reducing overdose risk and improving care for chronic pain patients on opioids. A central question drives today's story. Can society afford not to protect American lives, and are we willing to renew public health investments that support clean air and healthy living? Since the Clean Air Act, the EPA has used the value of statistical life to weigh health benefits against industry costs, with analyses showing substantial benefits and reductions in deaths each year. Historical examples from the Triangle Shirtwaist Factory fire to early 20th century pushes for safer working conditions illustrate that regulation can save lives without destroying industry. The piece frames the EPA's move as a moral and policy shift, not a scientific uncertainty, arguing it ignores well-established evidence that air pollution shortens lives. The change is presented as a setback to public health progress achieved over a century, recalling pioneers who fought for worker safety and environmental regulation. Supporting evidence includes the Harvard Six Cities study and similar research linking cleaner air to fewer premature deaths, fewer asthma episodes, and reduced heart problems and lost workdays. The author, drawing on public health experience, emphasizes the moral duty to protect lives and the risks of dismantling life-saving infrastructure. Notably, the Trump administration's EPA announced it would stop quantifying the economic benefits of lives saved in setting air quality limits, effectively valuing human life at zero in regulatory analyses. This episode keeps the focus on policy choices with real consequences for health, safety, and longevity in communities across the country. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.